Awesome. Thank you, everyone. Also, I acknowledge co-authors on this, Rob Caldo and Joey Stan, for their help in this put together. So we're going to talk about a few things today. We're going to talk about, one, why do UFPs matter? Our measurement apparatus and site locations. We'll cover some site-specific results that we got, and also answer the question we all want to wonder: is there correlation with what we're trying to do? So I think oftentimes we forget about why we're doing some of this work. So why do ultrafine particles matter? So one, what is ultrafine particles? Thank you very much. Thank you. They are defined, we typically define them as particles less than 100 nanometers in diameter. They're tiny. They contribute very little to the mass measurement and also have very little scattered light. So typically requires other measurement methods, such as a diffusion charger or condensation particle counters. Historically, those have been expensive, but the prices are coming down. Why do we care about ultrafine particles? There are a range of health impacts. This is kind of like the best hits of ultrafine. It causes reduced lung function, cardiovascular disease, myocardial infarction, aka a heart attack, heart failure, and also there's evidence of translocation to the brain. So we bring them in, and in the brain, I think we think about this like as an abstract idea. And there was a recent publication like 2 weeks ago that I thought was like, kind of blew my mind. They took people and exposed them for 1 hour to London roadway emissions, waited 24 hours, sampled their blood, simmed it, and this is what they found. They found on the images of the blood, nanoparticles attached to the red blood cells. And they showed statistical increase in that rate as the exposure happened. So it really highlights, I think we think of it as abstract, but like we're breathing these things in, and they're in our blood, right? And I don't think there's too many good things that can come from this floating around in our bodies. So what can low and lower cost sensors tell us about ultrafine particles? The question is, one of the questions we want to answer is, can we use optical particle number count to infer information about the UFP concentration? So we're all familiar with the classic particle size distribution, which I forgot back over here, but typically we see a nucleation mode and an accumulation mode. But the question is, in that accumulation mode, it does extend into 100, 200, 300 nanometers. These low-cost optical particle counters and advanced photometers or PM25 sensors do provide number concentration. They claim they can do 0.3. Can they be a clue about what's happening in the UFP space by just inferring that small edge of the distribution? The other question is, can measurement of solid total number count greater than 10 nanometer provide us more insight about sources? So some technologies are catalytic strippers. If you're not familiar with a catalytic stripper, it can take volatile, semi-volatile, and solid aerosols pass them through. The volatile fraction will be removed by oxidative catalyst, so it turns to water vapor and CO2, and out comes just the solid particles. And then the broader question is, can a suite of this instrument provide a rich picture about ambient total number count? If you combine these opticals, you combine ultrafine particle measurement, you combine the solid fraction measurement, what does it tell you? So that's what we're going to try to answer. All right, so let's take a look at our high-tech but low-tech measurement suite. So we took a bunch of low-cost sensors. So we took an AlphaSense OPC-N3, which is an optical particle counter, capable of resolving 0.3 to 40 micron with PM data as well. Did the Piera IPS7100. This is a new sensor to me. This manufacturer claims that they can do 0.1 micron, down to 0.1 micron. I am not here to judge either way. I'm just saying what they say. I'm not convinced that's possible, but we'll just test it anyways. Also gives PM data as well. The classic Purple Air, which uses the Plant Tower PMS 5003 sensor, claimed again can provide count data from 0.3 to 10 micron, and then we also use the OpenCPC. This is a condensation particle counter that can measure from 10 nanometer up to 1 micron. That's going to provide that ultrafine measurement. We were high tech. We put it in a plastic tub. We cut a hole inside, put a fan on one side so you bring in constant fresh air, put a lid on it, stuck it outside. We did the data communication through a Raspberry Pi. Basically, all the USB data got dumped to the Raspberry Pi, and then over Wi-Fi, it just dumped it to Google. It really highlights that complex measurement systems don't need to be that crazy. It's pretty easy to do it. You can just stick them in a plastic tub and stick them outside. Although, caveat, we'll learn some lessons about why are there some reasons to do something a little bit different. So solid particle measurement is kind of interesting. For those not familiar with solid particle measurement, we use an oxidative catalyst, an instrument from Catalytic Instruments, to remove the volatile fraction from the aerosol. So these devices work by, like we said, stripping the volatile fraction, converting it to CO2 and water vapor. One of the challenges when working with the catalytic stripper is that they have diffusion loss. So in the far right plot over there, you can see that the device itself has some diffusion loss because of the internal flow structure. And so to make a system be able to measure solid fraction, you can use a diffusion dummy or diffusion tube, which basically just use a long length of tubing to match that diffusion loss. Because of that, we have a switching valve. So the OpenCPC is basically operating the switching valve, measuring basically upstream of the catalytic stripper with that diffusion loss, and then downstream to get the solid fraction measurement. One of the challenges, this design was for 1.5 liters per minute. our CPC only is 0.5 liter per minute, so we had to make use of makeup flow, so we just used a pump to pull an extra 1 liter per minute, connected it over via Raspberry Pi, and then dumped that data to Google. Now there's kind of one interesting thing is in the bottom right corner, we have a plot of kind of what this looks like. So in the bottom left, with the catalyst off, setting ambient air, and that switching valve operating, the solid fraction is at unity, meaning that the diffusion loss in the tube is the same as the diffusion loss in the instrument, the catalytic stripper, and so you're getting unity, and that's what you'd expect. We then turn it on, you see the solid fraction drop. That's because we're starting to remove the solid versus the volatile fraction from the aerosol, so the solid fraction is dropping down that we can measure, stabilizes. We hooked it up to some sodium chloride, it goes up to 0.75. Well, why not 1? So there's another mechanism of loss in catalytic strippers, and that's thermophoretic loss, and that's because you heat the sample up to 350 C, and you gotta bring it back down, and so the thermophoretic loss on that, math basically works out to about the highest you can get is about 0.75, so the sodium chloride aerosol kind of matches that, and then we dumped it back to ambient air, and you see it drops back down. So that's the solid measurement. Site locations, 3 locations. We did a urban residential neighborhood with close proximity to the freeway, 35W, in Minneapolis, flight path to MSP Airport, and we monitored for 8 days from September 11th to September 19th. Site 2 is a suburban residential location with no real nearby industrial sources. And the last site is the OpenAeros headquarters in St. Paul. We're on a commercial zone, less than 50 meters to a very busy trucking lane. On the backside is a very busy rail line, and we stuck it up on the roof. There's a picture of them hanging out in their plastic buckets from October 6th to October 11th. Fresh data. So let's take a look about what is this from a raw level, or from a very quick high level. We won't go into too much of the diurnal trends and all that stuff. We're just gonna look at correlation, but here is a plot. At the top is the optical particle number count, greater than 0.3 from those 3 sensors. Below is the CPC, the ultrafine measurements, both the solid upstream of that diffusion tube, the OpenCPC measurement, and then the black line at the bottom is the solid number count. And you see first, there is definitely trends of transient peaks that are happening in the optical count. What is very interesting is that in the ultrafine, it is happening at a much higher frequency. In fact, one of the things that's interesting is that with the 1 Hertz data, this is subsample to be 5-minute average. If you look at the 1 Hertz data, there are periods within there that you have spikes of 30-second bursts that are happening every 2 minutes. I couldn't correlate what they were, but didn't appear to be aircraft related. It might be that the wind direction is picking up stoplight traffic that's moving every couple minutes, but it's very interesting to see these very high-speed transient events. So how do we kind of make sense of all this data? We're going to use a Pearson correlation table. Now you're saying, oh, there's so much data here, and how am I ever going to look at this in one slide? So let's break it down really quickly. So first, let's look in the bottom left corner. The bottom left corner is, how do the optical particle counter number, PM2.5, or for one device, 0.1 micron, how do they compare to those UFP concentrations? And the answer is, they don't. The Pearson coefficients here are pretty much 0. So meaning that the measurement of ultrafine versus optical particle count, PM2.5, even for that one that's claiming 0.1, there is no correlation. Up here, we're looking at the correlation between just the OpenCPC versus the one that was connected to that diffusion tube, but we do see very tight correlation, meaning these two systems are measuring roughly the same thing, even with that little addition of the diffusion loss. Bottom right corner, how do the optical counters compare to themselves? Generally really good. With the exclusion of the OPC in 3, its PM2.5 is a bit lower than that, but you're generally seeing number counts correlating between all of the devices. So they're all measuring the same thing, but when you compare them to ultrafine, they're not measuring that. Let's take a look at site 2, different site. This one's kind of interesting. Again, we see these trends of temporal variation, but the ultrafine temporal variation is much tighter. I will say that you notice that the black line stops a little early in that one. We lost some data because it was a strangely hot October, about 90 degrees. You're in a plastic tub in the sun. We made a greenhouse. We melted the pump. We were running at full blast, and it just masked. It melted down, so we lost some measurement there. But we can infer some information from that prior to that. Again, we can use the Pearson correlation table to do it. I will point out there's one really interesting, we do have a mouse, excellent. There's some interesting information here that happens. We see a huge increase in the optical number count, but also an increase in the solid number count and ultrafine. And that event happened on a Friday night, and there is a neighbor that lives nearby, and the wind direction is just right, that it is very likely that they had a bonfire that night, and they're notorious for not putting them out. And so it's kind of interesting that we see a very interesting trend that you're seeing some combustion-related events that you can start to defer from the solid fraction measurement. So what does the Pearson correlation table look like? Pretty much the same as the other one. Bottom left is our OPCs versus ultrafine. There's no correlation. Bottom right, how do our optical particle counters compare? Same thing, pretty good, except for that PM2.5 on the alpha sense. And upper left is the 2 CPCs on that diffusion tube, and they're in agreement as well. So site 3, is the OpenAeros office up on the roof. It's in that commercial district. Again, you see temporal changes in the OPC count, but the frequency happening in the ultrafines on the bottom plot, much faster. What is interesting is that what you do notice is that if you look at the solid fraction, that black line, and you look up to the optical count, they look pretty similar, and that's pretty interesting. There was another event that happened that Friday night. There was a fire north of our facility. At the very end at 10:11 over here, I got a mouse. You can see that, again, we have a climb in the optical number count. We have a climb in our solid fraction. It's hard to tell from the ultrafine because there's a lot of noise, but there is a fire that was observed. We also pulled the purple air data from a device that was about 8 blocks away. This is that same data set in magenta, also detected. So what happens when we look at the Pierce correlation table here? Same thing. This time we see even less correlation, so again, they're all 0 for ultrafine versus particle number count, PM2.5, et cetera, et cetera. Optical counters all agree with each other. We're not seeing that, again, when we see the N3s, the PM2.5 values are pretty low. Not as good a correlation between the two CPCs this time in terms of with that diffusion tube, so that might indicate there was some particle loss that was impacting it. But what can we abstract from this? And I think this is the hardest thing, is like, okay, we have all this data I talked through, but like, what is this telling us? I think the takeaway from this is, if you look at all three and abstract the image out to just looking at a heat map, you see the same trend. All three sites show very poor correlation between ultrafine particles and optical number count. The optical particle counters themselves, between themselves, pretty consistently good, but you do see that PM2.5 value, that lighter yellow value showing up. So again, the highlights, it's pretty repeatable. But what is really interesting is the middle, which I didn't talk about, which is the solid fraction correlation. And what you see is that the solid fraction correlation is changing from site to site. What that means is that it's providing a unique aspect about telling you about the sources in that space. So it is a nice piece of information that's giving you a clue about what's happening. So what can we conclude? Well, from these three sites, that ultrafine particle and 0.3 micron from the optical common data that we had showed no correlation across those three sites, and really needs to measure these things independently. You need to measure ultrafine, you need to think about measuring mass data with optical counters or number counters. Solid UFP measurements show weak correlation with both UFP and 0.3 optical, depending on the site and depending on the unique and independent measurement. So it's telling you that solid fraction is giving you another piece of the puzzle about what's happening in that space and what the sources are. And yeah, so that really highlights the differences in correlation, or really highlighting the uniqueness of each location in terms of sources. And what does this mean? Is that you kind of have to measure. One of the limitations of our design is that we didn't do them all at the same time. We had to move the site around. And so as we think about reducing cost of instrumentation, what that allows you to do is get more spatial resolution. You could have, as you bring costs down, we can expand the number of sites that we have. So if you can get a third of the cost, you can get 3 times more spatial resolution. You could have done this at the same time and probably answered some more information. So I think it really highlights that as costs come down, we can get a much more rich picture about what's happening, especially in the ultrafine space, and provide different pieces of information about what are the possible sources of those ultrafine particles and just particle generation in general.
Do we have time for one quick question?
Question, Aaron.
Sure, go ahead.
So you stuck your stuff into a plastic tub and you put a fan on it?
Yeah, that is correct.
And so you're trying to compare ultrafine particles with big particles, and so.
Yeah, it's a good question. So do we have a lot of particle loss in so?
And also based on their placement within the box?
Yeah, so I think if you were to look at like PM10 data, I would certainly say you don't trust our PM10 data. You could have some influence of that. In general, the velocity counters that we're working with are very slow, so we should see consistent placement. And I think that the optical counter being so tightly correlated is matching that. That the optical counters are seeing the same things. If you look at the PM2.5 data, they're also correlated. So I think it really indicates that for the size that we're looking at, it was okay to do that. I would not do this with like large coarse mode aerosol. You're gonna have tons of sec. But for really small stuff, and especially the ultrafines, diffusion loss and stuff like that is really minimal in our plastic tub of goodness.
But there must be like a limit, like 100 nanometers, maybe like 10, because you said your OPC goes down to 10. Would 10 have more issues?
Yeah, good question. With the CPC, which goes down to 10 nanometers, that has seen more. I think that in general the diffusion loss would be pretty small in the tub because the transit length is pretty short.
Okay.
So like the answer is probably yes, there's some influence on this. And this was just a quick way to get some simple experiments and put them in a tub. And they sat outside in the rain and in the sun. I maybe wouldn't use a clear tub because you make a greenhouse, but I think it highlights that instrumentation in suites like this don't have to be like super complex or fast measurements if you want to do something fun.
Let's thank Chris for your time.